much. Good morning, everybody. My name is Nicolas. I'm currently employed at JP Morgan, where I spend most of my days trying to make complicated code much simpler, while a bunch of people gleefully do the exact opposite. So I am aware this is a very good modern take on the punishment of Sisyphus, but let's be honest with each other. Most of us here probably won't write code for a job, or worse, as a hobby, and you don't do that for any length of time without developing a special relationship with pain. I want to talk today about data types modeling, because I think they're at least half the battle when it comes to writing simple code. If you get the types wrong, no matter how much work you put into it, it's probably going to end in tears, because, well, specifically my tears, as I have to maintain it later. But if you get them right, then it's going to be a lot harder to make a mess of it. A lot harder, mind, not impossible. I do know some very talented people. I feel like I'm qualified to talk about this because I have a fair amount of experience in it. Now, just to disambiguate here, I'm not saying I have a lot of experience in getting things right. I've been getting it wrong for close to 20 years, and I've been trying to get it sort of rightish for a few years now only, so I have a lot of experience in getting things wrong, and this is what I'm going to be talking about today, all the entertaining ways I've gotten things wrong. And as we go, I'm going to try and fix them, and hopefully land on a solution that, with the current state of my knowledge, is the best way I know of. You're going to have to wait until the end to know what the solution is. I'm not going to spoil it, but yeah, this is what we're going to learn. Now, before we get started, I have a bit of a backstory to give to this talk, because it is one of these annoying talks that start with a personal anecdote to make you relate with the speaker. When I was starting to work on that talk a few years ago, I was telling my family how I had gotten some feedback on some work I'd done, and how my examples tended to do a very good job of taking good, interesting material and making it really boring. So my son, who's a lovely boy, told me not to worry about it, because for my next talk, he would be the one to pick the example. Now, he's half Japanese and was 5 years old at the time, so today we're doing Gundams. Do we have any Gundam fan in the room? Yeah, I was hoping not. So I have to be completely honest with you. I probably don't know as much about Gundam as I should, given that I'm actually giving a talk on them right now. I did try to research them a little. I really quickly found out that sometimes they can grow wings, and then you have to call them Gundam wings. So I went, well, that's about enough of that, and I stopped on the ground that it was rubbish. So it is not entirely impossible that this might not be entirely faithful to the Gundam lore. I'm going to do my best to avoid offending you, but yeah, right. Well, with that out of the way, as we all know, Gundams are giant robots controlled with Super Famicom gamepads. We all know that, right? Anybody who knows anything about Gundam knows that. And the thing we do with this Gundam, with a remote controller, we can send commands to the Gundam. And there's a finite set of commands, legal commands that we can send. We can tell a Gundam to change direction with a face command. We can tell it to face north, and that's going to make him face north, face west, south, and east. Probably didn't need to do all these animations, but I really wanted to show you how good I was at pixel art. And then you can tell them to start walking and stop walking, right? Nothing too complicated here. And this is the entire set of legal commands that you can send a Gundam. Now there's a bunch of illegal ones you can send though. You could, for example, tell them to triple backflip, and the Gundam has no idea what that means. So he's going to be confused. And we all know what happens to a Gundam who gets confused on the field of battle, don't we? Gundams tend to have mixed feelings about this whole situation. So we are going to say this is an undesirable outcome, and we're going to try and make that not happen. And the way we're going to do it is, well, we have the remote controller, don't we? So we could use that to check whatever command is going to be sent to the Gundam and make sure no illegal command is sent. So for example, if we spot that and realize that -35 is not a legal argument to the face command, then we're going to reject it. And the Gundam is going to... Sorry, the mic is a bit odd. And the Gundam is going to leave to fight another day. So this is what we want to do. We want to check all the commands and make sure that no illegal command is sendable to the Gundam. And the way we're going to do that, we want all that to be checked statically, right? We want to look at a command and be able to say, this won't work. We don't want to run the command to say, well, this hasn't worked, because if it hasn't worked, then we've killed a Gundam, right? So we want to check it statically. And in order to check things statically, there's no better tool that I know of than types. So we're going to start designing types. First, we're going to represent direction. It's a fairly simple type, isn't it? It's a known finite set of values. We have north, south, east, and west. So the way I was taught to represent known finite set of values years ago in university was magic numbers. You open a namespace called direction, and then you stick a bunch of values in it, all of them integers. And then you give them arbitrary values. Could be anything. They just have to be distinct. So you could, I don't know, you could use 40U or 1024, any funny number you can think of, and stick it in there. They just have to be distinct. And that, when I was learning how to program, was the state of the art, at least in the industry. Of course, there's many flaws in that design, and one of them becomes apparent quite quickly, but I need to make a small parenthesis before I explain why. I don't know about you. I don't know how you debug code nowadays. I used to use debuggers. They were really cool. But nowadays, whenever I start writing code and I want to debug it in production, I have to connect it to so many different VMs. The code is not running on my machine. It's a lot of work, so I reverted to print line debugging, which I really enjoy. But when you have that, if you print line north, it's going to print 1. That's not useful. I don't remember all the values of all of my things, right? So what I tend to do is to write pretty printers, like label here. Takes a direction. That's a confusing type. That's an int. It could be any int, but anyway. And then the implementation is fairly straightforward. You just pattern match on it and provide a valid legal label for all of the possible values. Now, that seems reasonable. What do you think happens when I run that, though? Well, minus 35 is a valid int. So label takes an int, it's going to accept it. The compiler is going to be very happy with it. And we're going to have another runtime explosion. So that's not a good solution. When I figured that out and talked about it with my tech lead at the time, he told me, of course that doesn't work. You have to use type aliases, you idiot. So fine, Scala has type aliases. I wrote a type alias, direction. Direction and int are the same type now, which allows me to do this, which is quite nice, because now it's a lot clearer what these things are. They're not ints, not any ints, they're directions. And it allows me, it's even better here, because now label is a lot clearer about what he expects, isn't it? Now, it is a lot clearer for a human reader. As a human, I understand I should be passing it a direction. But as far as the compiler is concerned, though, there is no difference between that and the code I wrote before, because direction and int are the same type. So that's still going to compile, run, and blow up at runtime. So type aliases are not great. But for a while, this is the best we had. And then, quite a while later, Java, which was the language I was using at the time, made a massive breakthrough, and it invented enumerations 20 years after C, I think. So that was a good effort. And so I was told, well, even though enumeration didn't exist until yesterday, you should have been using them the whole time. Go and fix your code. That was my tech lead at the time, and yes, I am still a little salty about that. But I did enumerations. We have enumerations in Scala, which start by removing a lot of code, which is always nice. And then you do some weird thing, honestly. You have to extend enumeration for some reason, and then you get that. I don't know what that means. We'll see very soon why I didn't bother to learn, because Scala enumerations are rubbish. But that is what you do. And now we can fix this. Well, fix, really. Now the type is direction.value, so that's not a good type. It's not a bad one, but it was weird. I don't want to work with direction.value. I want to work with the direction. But if this is what it takes to save Gundam kind, then, let's do that. And now this doesn't compile any longer, does it? Because minus 35 is an int. It's not a direction.value, so we don't actually kill a Gundam this time. Now, to get back to my whole example of debugging, when I print line debug, what I tend to do is comment out a large chunk of code to see what happens. Now, it's not random. There's an art to it, right? But here, let's pretend. I just commented that out. The compiler is still very happy to compile that, though, right? That's not a problem. What do you think happens when I run that? Well, direction.west is a legal direction.value, isn't it? So the compiler is going to accept that and blow up my runtime, because my pattern match doesn't handle the case. So when I figured that out, I thought, right, I did what any good developer would do, really. the standard implementation of the feature I need doesn't quite work the way I wanted, so I'm going to reinvent the wheel and roll out my own, like everybody would do, right? And so I wrote my own enumeration. A trait in Scala is basically a fancy abstract class, so just that's an abstract type direction. And then in a namespace direction, I would create 4 values, right? So now I have direction, which has 4 inhabitants, north, east, south, and west. Step forward, because now I'm back to direction, which is a better type, in my opinion. And that still fails. And that is annoying. Now let me explain to you what it fails. It's a little weird, it's a little quirk of the Scala compiler. See, in languages that have pattern matches, you sort of tend to expect the compiler to check your pattern matches for exhaustivity and let you know when you forgot a case, don't you? And the Scala compiler certainly tells you it does it, most of the time, except sometimes it won't, and it won't tell you it hasn't, it will pretend that it has. So that can be a little confusing, and sometimes you will get, well, you get Gundams that explode because of it. Now, the reason it does that is really frustrating. See, the thing is, while the compiler knows your pattern match is non-exhaustive, because it knows that direction.west is a value that exists, that you haven't handled, since it will not be able to prove exhaustivity, it won't even try. And the reason it won't be able to prove exhaustivity is because while it knows of all the possible values statically, it does not know of all the possible values it might encounter at runtime. Because this might be compiled and bundled as a library and used in another software that has declared a new implementation of direction, like northwest, for example. And so the compiler does not know all the values the pattern match might encounter, and as a result, doesn't even bother to try and prove exhaustivity, which is very annoying. However, that's quite easy to fix. We can mark our abstract class as a sealed, which means no subtype of direction can be found anywhere outside of this file. So with that, the compiler knows that these 4 values are the only possible values you can ever encounter of direction, and refuse to compile that with a useful error message. It's not quite Elm, but you do get, it would fail in pattern case west, which is quite nice, right? So before we go any further, quick recap. What we've learned so far, we've learned that enumerations make nonsensical values impossible to represent, which is nice, right? You can't write commands that will blow up a Gundam any longer, not commands, but directions, because you can't write something that doesn't make sense. They also guarantee that our code handles all necessary cases. So a lot fewer surprises at runtime because you have handled all the cases. That is, of course, only true if you're not using Scala enumerations because they're rubbish, so don't use these. Right, now we're done with direction, but direction was just one of the 2 components we had to model, right? We had direction and commands, which are phase, start, and stop. And the way I was taught to model that, and I'm sure you're going to have a laugh, nobody writes code like that any longer, except everybody I know. You create a struct command, which has 2 fields. The first one, which is going to be an order, typed as a string, because why not? Which is either phase, start, or stop. And then an optional direction. Because some commands have a direction, phase has a direction, but start and stop don't. So it's not compulsory, it's optional, right? That, I was told, is the way to do things. So there's many things that go wrong here. The first one is obvious. What do you think happens when I send triple backflip? Well, we've seen that, haven't we? The Gundam doesn't like it. But we know the fix for that, do we not? We know that the commands are a finite known set of values. They start, stop, and phase. That sounds a lot like an enumeration, which we just invented, so let's do that. Exactly what I did before, a sealed trait with namespace in which I put all possible values. And then I get to do that. Now, I'm not using a string any longer, I'm using an order, and this becomes completely impossible to write, because I can't pass a string, I have to pass a legal order, which is nice, right? We've made a step forward. That can be replaced with this, for example, which is completely valid and also doesn't make any sense. Because start south is not a valid command, right? Phase south is a valid command. Start south, you could think, well, that probably means phase south and start, but you don't know that. This is non-specified, it's not a valid command. So the Gundam is going to get confused and blow up again. This is something you want to avoid. And the problem we have here is that we have defined it in such a way that start can take a direction, and it's also possible that phase might not. And we want to change that. We want phase to always take a direction. So let's modify order and say, well, it's not an object any longer, it's actually a record that contains a direction. With that, it is now impossible for face to not contain a direction. And it's also impossible for start and stop to contain a direction. So I'm still calling that order, but isn't it exactly what we wanted to model? That is exactly command that we wanted. We have start and stop, and face with a direction. All possible states, no stupid state. Pretty good. And now that is impossible. That will not run. That, on the other hand, will. And we have a Gundam that leaves again. So that's pretty good. What have we learned? We've learned that enumerations are absolutely everywhere. They're the first tool we reached for when we encountered a problem, right? Immediately we needed enumeration. But then realized sometimes they're not quite enough because we had to tweak it slightly to make it work. However, something like an enumeration might be, because what we invented is very much, it feels similar to an enumeration, doesn't it? It's not quite an enumeration, but if you think about it a certain way, it might be like enumerations might be a specific case of what we just invented, and maybe we invented something more general than what we had. Right, now that we have all that, one more thing I'd like to do, because when you have an API that works, it's always good to try and make it composable, because composition is the root of good API design. So let's try and see how we can go about composing commands. This is what we can do at the moment, send one command. What I would like to do is to send bunches of command, chain command, like this. And for that to be one command that we can send to the Gundam, and the Gundam will run. So I want to be able to say, face east, start, and stop in one go. I want that to be just the one command. And as is often the case, the answer is in the question, isn't it? Because I just said, I want chained command to be a command. So what I'm going to need to do is to create a new variant for our command and say, right, chain, which is a composition of one command and another. And that's really all there is to it. Now, we have chained commands, and we can even write some. Yeah, dreadful, isn't it? If you sort of squint, you can see that we're telling the Gundam to face east, start, stop, then face west, start, stop. You're probably not having a great time reading that. I had to write it, and I didn't like it. So I'm not doing that any longer, especially since I don't really have the screen real estate. So what we're going to do, it's a sport that we really enjoy in the Scala community. We're going to write a DSL for that. The syntax is irrelevant. What this is doing is, if we have a command, we can squiggly arrow it into a second command and get a compound of the two, right? And when you write a DSL, it's often good practice to give smaller terse aliases for the terms of your language. So like that, start, stop, and face, and the directions, right? And that allows me to create this function, move, which takes a direction, faces it, starts and stop. And that, now move east followed by move west, is the entire whole page of code I showed you earlier. So that's quite a big step forward, I think. And when you run that, it actually does exactly what you'd expect, which is nice. And, well, we're pretty much done with that type, aren't we? What we've done here is we completed the data structures by using records, chain and face are records struct. I'm sure you're familiar with the concept. Sort of enumerations, but not quite, common and direction, which are like enumerated types, but not really only that. And we also had to make our data type recursive, because command is defined in terms of command, because chain contains command, and command is a command, right? And all of that is called an algebraic data type. So let's try and give a proper definition for that. We've seen that command was either a face or a start or a stop or a chain. And this notion of or has a name. That's called a sum type. A sum type is a discriminated union of values and can be thought of as an or on types, right? We have all these things. Now, some of you might still be paying attention and wondering, hang on a minute, what's that word doing here? And you're completely right. I haven't earned the right to use discriminated. I haven't explained to you what it was. I've used it, but I've not explained. So let me explain now. But in order to do that, I have to show you what an undiscriminated union is. And in order to do that, I have to write a little bit of C. So any of you who's done what I'm about to do in C, I'm sorry, I might trigger your PTSD here, so you might want to stop listening for a few minutes. It's only going to last a few minutes. And for the rest of you, welcome to hell. This is what we do. A union, int or string, is either an int or a string. So far, so reasonable. That's all right. Then I want to print it, right? Print union. No idea how to do it, because I know it's an int or a string. Don't know which one, though. That's not very useful, is it? So, in order to know what it is, well, we have to manually keep track of it, which is not fun. Because then what you have to do is do, oh, look, an enumeration 20 years before Java, which I call type tag. And we either have an int or a string. So this is used to keep track of what value we have, the type of value we have. It's either an int tag or a string tag. And then I update my union to say, right, it's also got a type tag. Call that discriminator. That's clearly intentional. We're talking about discriminated and undiscriminated. That could be a hint. And of course, what this type does right now is saying we have a type tag or an int or a string, which is not quite what we wanted. We want not the union of them, but the aggregation of them. So I'm going to make that into a record, a struct. And this needs to be nested in a union. So now I have a value that is either an int or a string, and then some other value which is telling me which it is. That's a lot of work, but it works, because then I can go back here, do that, because C is weird, and then the code all but writes itself. If I have an int, print it as an int, and if I don't have an int, print it as a string. That's that straightforward, right? That's reasonable. It really isn't, though. Did you see all the work I had to do? And also, I have to make sure that I'm going to keep the two in sync, that I'm never going to have an int and my type as a string, or vice versa. And I have crashed many production systems because I got that wrong. It's very easy to get wrong, especially if you start having threads and stuff like that, and then you need to have some sort of semaphore to prevent interruptions in the middle of it. It's a nightmare. It's an absolute nightmare. But sometimes some languages have discriminated unions. They do all that for you. They keep track of everything for you, and this is how a pattern match works. This is how at runtime, the environment is going to be able to say, well, you're in that branch, so you just do that. So that is what discriminated means, and it's really very nice. It's a very good property to have. So that would be a sum type, and we know that command is a sum type. So an algebraic data type is a sum type, plus some stuff, because we're not done. We've also seen that command, well, chain was actually a command and a command, right? It's one value and another. And that's called a product type. A product type is an aggregation of values and can be thought of as an and on types. You already know product types. You might not have been familiar with sums, but products, they're struct, they're records, they're case classes. They're classes in Java. Every language has that. And so an ADT is a sum of products plus something more. We've seen that command was defined in terms of command, so command is recursive. And that's the last thing we need. An ADT is a potentially recursive sum of products. And it is such a powerful tool to have that Scala, after a mere decade, decided to have dedicated syntax for it. So all this stuff that we wrote is now much simpler, because you can rename that to enum, possibly not the best choice of name, because a lot of people now think this is an enumeration. That's not an enumeration, but that horse has bolted. It has caused some confusion, but we guess we have to live with that choice. And then you get rid of all that and all of that, and you have something which is not as terse as it could be, but much nicer. And to conclude this section, what we've learned is that algebraic data types are sum types or product types that are potentially recursive. And that really is the main thing I wanted to show you. And I have more stuff to show you, but if you remember anything from this talk is algebraic data types. Those are amazing. We're going to go slightly further now because, well, I might have been lying to you a little bit from the get-go when I said we can compose any two commands. That's not true. Some commands cannot be composed with each other. Take, for example, start and start. Well, the first start is all right, isn't it? It was stopped, it's starting, that's fine. But what does the second one mean, right? I'm already started. What do they want me to do? So that's going to cause a Gundam to get confused and blow up, as they tend to do very easily. Stop and stop is the same thing, isn't it? I'm already stopped. What do you want me to do? No, because there's a runtime explosion. And the worst of them all, which is start and face. So start is going all right, but then you're going to ask him to change direction. That's going to end up in a whole tangle of legs, and then we really don't want that to happen. So that's, again, something you don't want. What we want to do instead is we want to be able to make sure that you only compose commands that can be composed together, and we want to do that statically, don't we? We want to be able to know if the two commands compose together before we send them to the Gundam. Because if we have to run them in order to know whether they're valid, then we're going to get the Gundam to blow, so we don't want to do that. And again, the solution is in the question. We just said, I want to be able to keep track of the state at the type level. Well, in order to do that, you need a type, idle and moving, which represent the possible states of a Gundam. And if you have this information, well, you can do that. You can index command with these two type parameters, before, which is the state of the Gundam before the command can be run, and after, which will be the state after it's been run. So here, phase is idle to idle because you're not actually moving or stopping. Start goes from idle to moving, and stop goes from moving to idle. Those are straightforward. This one is a little more complicated, and it's also where most of the magic lies. So the first command is going to go from one state to another. I don't know which one, A to B. But then you have to think hard. The second one, where can it start from? In order for that to work, we need to make sure that the second command starts from where the first one ends, don't we? So we want it to be from B to C. It can be any C, but the B has to be fixed. We have to have two commands that commute, don't we? So that gives us the entire type of that. That's going to yield a command from A to C, because we don't really care about B any longer. We go from A to C via B, certainly, but that's a mere detail. And we need to declare the data types. So that's pretty straightforward. We have what we wanted. We need to update our DSL quickly by adding the data types, right, or the type parameters. But that's all. We just had to type it properly, and now everything works. And this doesn't compile any longer with a helpful error message telling us, well, you have something from idle to moving, and I need something from moving, so that doesn't work. So that's great. Similar for stop or for start and face north. None of this work any longer. Now you might think, yeah, you just disabled everything. No, I haven't. This works, right? Because all of the state transition are legal. So that's going to work, and the Gundam is going to run the whole thing. You might think, when we did first invent algebraic data types, we had some interesting properties for pattern matches. Do we have more interesting properties for pattern matches with what we've just done? So in order to check that, I'm going to say, I need to be able to print a command that starts from the state moving for reasons. We need that. I need it for the explanation, which is a good enough reason. And I have two cases only, right? It starts from moving, so we can only have stop and chain. I cannot have start and phase because they both have a before parameter of idle. So these are the only variants that I really need to handle, and the compiler is going to be only too happy to accept that. But we also have discovered the Scala compiler will sometimes tell you, yeah, that's fine, I have checked it, but it hasn't. So let's check whether the compiler actually does anything clever here. First thing, what do you think happens when I do that? Well, that doesn't compile, which is good, because start isn't a command from moving. It's a command from idle, and the compiler knows how to handle that. So that's great to have found that. This is exactly what we wanted. I'm doing my usual thing of commenting things out to see what breaks, and here the compiler breaks. It's telling me you need to handle chain with a very precise error message. So that is nice. The compiler is not pretending that it's checked my code. It has actually checked it. And if I were to uncomment that, and for whatever reason handle start, because I was tired, say, then the compiler is going to tell me, yeah, no, don't do that. Start is not a valid value of your type. Don't handle that case. There is no point in it. Which is nice, right? The compiler is telling me not to do some work. That some code I'm about to write is not necessary, and the best code is always the one I don't have to write. So this is great. I like that property. What we've learned, if we use type constraints on our sumtypes member to make illegal state transition impossible to represent, and guarantee that our code handles all necessary cases, but only necessary cases, which are all very interesting properties to have. What we've just done is, it's called a generalized algebraic data type. I don't know why it's called generalized. I've read explanation, they didn't make sense to me, so I'm just going to call that generalized algebraic data types, GADT for short, and I'm going to try to give you a simple definition of it. It's not going to be that simple, but you're going to get the intuition. We've seen that command is a generalized algebraic data type, and it's a sum type, so that's got to be part of the definition, right? Command is one of these, phase, start, stop, or chain, so it is a sum type. So a generalized algebraic data type is a sum type plus complexities. The first complexity is this. We have added type parameters before and after, which only exist at the type level. You don't have values of type before, of type idle or moving, and encode a very important property of your data type at the type level. Well, that's called a witness type, right? a witness type describes the property of the sum type's variant at the type level, which is exactly what before and after are. So a GADT is a sum type with one or more witness types. We had 2 before and after. You could have 1, you could have 100 if you wanted to. You could. You don't, please, but you could. And finally, well, the compiler does some pretty funky things here, right? It knows that the first parameter must be equal to moving. And when saying that, well, the absence of that branch of the pattern match, the compiler will be able to say, right, I can produce a value of type command of where the first parameter is equal to moving, and that is not handled here. So it's going to be able to have some sort of equational reasoning based on equality to say that's missing. Similarly here, command.start, it knows the first parameter, that's idle, that's not equal to moving, so the compiler is going to complain. All of that is a very hand-wavy way of saying, here the compiler has been able to reason equationally about types and use type equality in order to get to conclusions. That's called type equality. It is information available to the compiler about each witness type, allowing it to refine pattern matches. And that gives us the entire definition of GADTs. It's a sum type with one or more witness types, each equipped with a type equality, which is a very complicated definition, right? It might not be that useful, but it's what we learned. Now, the way I prefer to think of GADTs, because I'm not necessarily intellectually equipped to deal with that, it's just I prefer to think of it as a sum type with interesting properties for pattern matches. And that's good enough, right? So that's a good intuition to have. It's completely incomplete, but it's enough unless you're writing compilers. How much time do I have left? 10 minutes. All right. I don't know whether, because this is everything I wanted to show you, but I have some bonus material in case I spoke too fast, which I apparently have. So I thought it would be a bit daft to give an entire talk on algebraic data types and not tell you why they're called algebraic. It feels a bit unfortunate. So I want to talk about the algebra of types. I don't know if I can do it in 10 minutes. So when you stop me, either, well, afterwards a lunch break, so maybe I can overrun a little. And if you don't want to listen, you just go and feed yourself. Or I could stop here, but I don't want to, so I guess I won't. Right, the algebra of types. In order to talk about the algebra of types, I need to introduce the notion of type cardinality. It's pretty straightforward. The cardinality of a type is a number of inhabitants this type has. So for example, nothing. How many values does nothing have? Well, very well. By definition, nothing has no values. So it's got a cardinality of 0. Yes, thank you. Well done. Unit. How many values in unit? 1. So cardinality of 1. Boolean. True, false. That's 2 value, yeah? So it's got a cardinality of 2. You get the idea. Now, let's talk about the cardinality of sum types. But in order to do that, I need a sum type. So let's write one. I'm calling it plus. And we either have a left of A, which contains an A, or a right of B, which contains a B. And the reason I've decided to use plus rather than a human readable identifier is because in Scala, when you have a binary type constructor like that, it can be used in infix notation, which I think looks great on the following slide. So, what is the cardinality of that? Well, we have all the A's inside the left, and all the B's inside of the right, yeah? So the cardinality of A plus B is all the A's plus all the B's. The cardinality of the sum is the sum of the cardinalities, which one might think may be why they got this name in the first place. And I want to play a little bit now with that, to show you that all the algebra you've learned, all the way you've learned the addition worked, carry over here. But in order to do that, I need to introduce a complicated word. I need to tell you about type isomorphisms. We'll say that type A and B are isomorphic if they have the same cardinality. And we'll write it like that. Now, what does that actually mean? It means if you have two types that are isomorphic, if A is isomorphic to B, it means you can always take an A, go to a B, and back to the A without any information loss, right? So you can always go from A to B and back to A, and from B to A and back to B. And if they have the same cardinality, this mapping to go from one to the other and back is trivial because you just line all the values in a consistent order and map from one to the other, right? So that means it's irrelevant which one you're working with. You could work with A or B. It doesn't make any difference because semantically they're the same thing. You can just cast from one to the other without a problem. Knowing that, we can do some pretty fancy algebra here. We're going to do 1 plus 1 equals 2. And that carries over to types with very straightforward translation. We're going to say, we're going to map a number to a type with the same cardinality, so 1 to unit and 2 to Boolean. Plus is going to be sum, and equality is going to be type isomorphisms. Yeah? Now, just to prove that it works, let's do the mapping. Unit plus unit is either a left of unit or a right of unit. Boolean is true or false. The mapping from one to the other right here, right? You have the same number of values, so you can easily map from one to the other, and you can transform one into the other without a problem. And this property carries over to everything you could think of. Addition is associative. I'm not going to pronounce that. It's never ended well for anyone who tried to pronounce associativity out loud. You just can't pronounce a parenthesis. It doesn't work, so you can read that. But it carries over to the types. It's easy to show, right? The top one is either a left of A, or a right of a left of B, or a right of a right of C. 3 values. And then here we have left of A, left of right of B, right of C. We just map from one to the other, and we have a mapping that proves that these 2 types are essentially the same. Sums are so commutative, you can flip the order of the operands. That carries over to types, which is easy enough to see. Left of A, right of B, right of A, left of B. Draw the arrows, it works. Yeah? And finally, addition has a neutral element, 0. If you add 0 to any number, it's still going to be that number. Well, if you take the sum of any number and nothing, you're going to get that type. Right? Because A plus nothing is either left of A or, well, nothing, right? You can't have a nothing, you can't have a value of type nothing, so you can't have a value of left of no value. That doesn't exist. And the bottom one is an A, so you just map the A's to the left of A's, and you're done. Right? So those are isomorphic. We've done sums. This is all I wanted to show you about sums. Let's do products. And in order to do that, I need to write a product type, which I'm going to call product. It's an A and a B, right, as a record. And then I'm going to do some syntactical magic to make it useful. So I'm going to say that if I have an A, I can take its product with a B, and that's going to yield the product of an A and B. That is, again, a binary type constructor, so I can use it in fixed notation, which looks nice, like that. So product of an A and a B. How do we compute the cardinality of that? Well, we have the first A and all the B's, and then the second A and all the B's, etc., until the last A and all the B's. So the cardinality of A, the product of A and B, is the cardinality of A times the cardinality of B. The cardinality of the product is a product of the cardinalities. And again, that might be a hint. Maybe that's why they're called product types, isn't it? And we can do some algebra again. Powerful stuff. A plus A is equals to 2A's. That translates very well to type level. The only thing we have had to add to our translation rule is we transform multiplication by the product of 2 types. Again, let's look at the isomorphism. A plus A is a left of A or a right of A. Boolean, and the product of Boolean and A is false in A or true in A. We can just map one to the other. They are the same type. I don't know if it's useful, but I find it really fun. And we have all the same properties as before. I'm going to go through them quickly because it's not that enthralling. But their product is associative, so product types are associative for exactly the same reason as before, right? You just map from one to the other like before. Same for commutativity. The product is commutative, product types are commutative. You can easily do that by looking at the mapping and drawing the arrows. There's nothing super interesting to be done here. And finally, the neutral element, 1. So the product of A and unit is A, which is a little fun, right? A and unit is just 1 of the A times unit. A is just A. You can just map to the one from the other like that. Now, we're done with products and sums. But we've seen that the definition of an algebraic data type includes one last wrinkle, haven't we? They can be recursive. So we're going to have to study the cardinality of recursive data types. Let's look at list, the prototypical recursive type. A list is either the empty list or the non-empty list, which is composed of the head of the list and all the rest of it, the head and the tail, right? And that is a recursive data type because list is defined in terms of list. And I'm going to want to study the cardinality of that. However, clearly, the cardinality of a list is infinite. Because whichever list you give me, I can always create a new one by taking an arbitrary A and stick it at the head and the rest as the tail. I don't want to work with infinite numbers. It is possible, but I'm really bad at it. It's counterintuitive, and also you're supposed to pronounce things like Aleph. I'm French, it doesn't roll off the tongue, so I'm not going to do that. Instead, I'm going to look first at list of fixed size, right? So when I use subscript like that, that means the list of size 0 of A. Well, we know what the coordinate of that is. It's going to be the coordinate of nil, because that's the empty list. The coordinate of nil is 1, because there's just one element there. So we know that. What about the list of size 1? Well, that's going to be an A, followed by the empty list. And we know that we can take the product out of the continuity, so we get the continuity of A times the continuity of the empty list, which is 1. So we get that. And we can keep doing that, right? For the list of size at most 2, you get that, which you simplify to continuity of A squared. You can keep doing that, and obviously you know where this is headed, right? The list of size at most n, the continuity of it is continuity of A to the n. That is interesting. How about now we study the continuity of a list of size at most something, right? When I use superscript like that, it means the list of size at most n. So what's that? Well, that's going to be all of the list of size 0 or 1 or 2 or 3 up to n. So that's going to be the sum of that, and we know we can take the sum out, and we know how to simplify that to this. And if you've done a little bit of math, you know that equation, right? That simplifies to this, which is really counterintuitive, but actually does work. And it's a bit odd, isn't it? We haven't invented division types that I'm aware of. We certainly haven't done it in this talk. And yet we're using divisions here. Again, I don't know whether that's useful, but it's kind of cool. Kind of like being able to do that. And let's make sure it works, right? That's if I use a large n or a type with a high cardinality, that's going to get big quickly. So let's do something simple. Let's do list of at most 2 booleans. Well, the coordinate of boolean is 2, and if you simplify that, you get 7. That sounds reasonable, but let's confirm it visually. List of at most 2 booleans. We have either the empty list, nil, or the list of size 1, which is true or false, or the list of size 2, which is true, 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 false, false, true, false, false. And if you count them, you get 7, exactly like we predicted. I don't know how useful it is to be able to predict that. I don't work in academia. Possibly people who work with type systems find that really useful. I don't, but I do find it really cool. And what we've learned here so far is that there's a deep connection between algebraic data types and the algebra you know. You can use this connection to prove fun facts about types. You can also use it to pad talks and look clever. And really, I think that's what I wanted to show you. So in closing, if you only remember one slide of this entire talk, this is the one to remember. Algebraic data types make data types simpler and safer. As we've seen, right? They make it simpler because you can't represent illegal states. So it's a lot simpler to think about them because all of the values are legal. You don't have to think, hang on, is this value legal? How do I make sure it's legal? You don't, it is. So that's a great property. It's also safer because you are guaranteed to handle all the necessary cases because otherwise the compiler is going to complain. So you know that you have a very stern teacher watching over your shoulder and telling you, nope, you have to do that as well, and that, which is sort of intimidating, but also very useful because then the code you write is a lot more correct than it used to be. GADTs do the same thing, only a bit more so. And if you think about data types that way, if you don't already, I'm not assuming anything, but if you start thinking about algebraic data types, about data types that way, that is going to have a lasting impact on the way you write code, and for the better, I hope. That really is what I want you to learn, how to think about types in a way that is simpler and safer. But if you have any question, now would be a good time to ask them. Thank you. There's a question over there.
Where? Oh, yeah. It's maybe not a question, but I wanted to add that in the C world, well, C++ world, they've added variants, so they have ADTs in C++.
Oh, I didn't know that.
Yeah. So it might be a cool addition to otherwise exceptionally nice talk. So.
Thank you very much. Yeah, I'll consider it, definitely. Thank you.